So these are the Chapter 11, Math 102 examples for the sections 5 through 8. And the first section is going to deal with probability with our fundamental counting principle, permutations and combinations. So we looked at those in the first 3 sections. Now we're going to look at probability with those. So we start off and we have Martha, Lee, Nancy, Paul, and Armando have all been invited to a dinner party. They arrive randomly and each person arrives at a different time. And how many ways can they arrive? Well, if we look here, we have 1, 2, 3, 4, 5 different people. So if they all arrive randomly, that's going to be, and we can't use more than one person at a time, so it'll be 5 factorial or like a permutation. And that will mean they can arrive in 120 different ways. Then they want to know, in how many ways can Martha arrive first and Armando last? So if I make 5 spaces for my 5 people. So Martha arrives first. We have 1 choice for first, and Armando arrives last. We have 1 choice for last. So that means for the second spot, because we've already used 2 people, we have 3 people to choose from. Then we have 2. And then we have 1. And when we multiply 1 times 3 times 2 times 1 times 1, we end up with 6. So now they want us to find the probability that Martha will arrive first and Armando last. We know that there's 6 ways Martha can arrive first and Armando last out of 120 total different ways. So that's our probability. And if you simplify it, you end up with 1 over 20. Okay, so here we have 7 performers, A, B, C, D, E, F, and G, and they're going to appear in a fundraiser. The order of performance is determined by random selection. Find the probability that D will perform first. Well, for this one, we have 7 total options. So the probability that D performs first, the first spot, we have 7 choices, and he is 1 out of 7. So it will be 1/7 for that. Okay, next we have E will perform 6th and B will perform last. So for that one, we need to first find the probability if E performs 6th. So we have 7 performers. So I'm going to make 7 spots. Put my multiplication symbol between them. All right, so E performs 6th. So there's 1 person there, and B performs last. So there's 1 person there. That means we've used 2 of our 7 people. So I have 5 people to choose from for the first spot, then 4, then 3, then 2, then 1. So when I multiply that all together, it is going to end up with 120. Now, I need to find the probability for just the 7 performers. I need to find that bottom number. So if they were to perform in any random order, it would be, and this would be like 7 factorial, because we have 7 to choose from here, then 7, so we have 7, 6, 5, 4, 3, 2, and 1. We're multiplying all that. And when we multiply it, we end up with 5,040. So the probability that E will perform 6th and B last will end up being 120 out of 5,040. Or if we simplify that, we get 1 over 42. Next, we're going to look at they perform in the following order. So C, D, B, A, G, F, and E. Here, they've assigned every single person a specific order. So we have 1 person for spot 1, 1 person for spot 2, 1 for spot 3, 1 for spot 4, 1 for spot 5, 1 for spot 6, and 1 for spot 7. So when we multiply that all together, we get 1, and it will end up being 1. The probability will be 1 out of 5,040. Our last one is F or G will perform first. So let's make our 7 spots. There's 4, 5, 6, 7. We'll put our times sign between them. All right, F or G perform first. So we have 2 people to choose from for first. However, we have 2 people to choose from here, but only 1 person can go. So that means for the second person, one of those people from the first spot that didn't get chosen will go with the other people. So we have 6 there, then 5, then 4, then 3, then 2, and then 1. So when I multiply that, I get 1,440. So my probability will be 1,440 over my 5,040. And that simplifies to 2/7. Okay, so here we're going to start off and we're going to get a box that contains 25 transistors, 6 of which are defective. And if 6 are selected at random, find the probability that all are defective and none are defective. Well, first we need to figure out how many ways can I select 6 transistors out of a box of 25. Now for this one, it's going to be a combination because order does not really matter the way I select them. So I have 25 total transistors and I want to choose 6. When I do 25C6, where I do a combination with taking 6 items out of 25, I end up with 177,100. That's going to be my bottom number. Now, 6 transistors in the box are defective. So I want to find the probability that they are all defective. So I really need to find out what's the probability of me drawing out all 6 that are defective. And if you want to, you can do a combination. It would be 6C, because there's 6 defective transistors, and I want to choose 6. When you do that, though, you're going to end up with a 1. So our probability here is going to end up being 1 out of 177,100. Now, we also want to know if all or none are defective. So to find that, we're going to do a combination again. This time, instead of putting 25 here, the number that are not defective are 19, because 6 of the 25 are defective. So that leaves 19 that aren't defective, and we're choosing 6. So when I calculate that, I end up with 27,132. So my probability there will be 27,132 over 177,100. And those are pretty big fractions. Unless my math lab asks you to, you don't have to simplify them. I would accept them like that. Okay, and then our last one for this unit, for this section, is going to be a state lottery is designed so that a player chooses 5 numbers from 1 to 30 on 1 lottery ticket. What is the probability that the player with 1 lottery ticket will win? And then what is the probability of winning if 100 lottery tickets are purchased? First, we have to figure out, well, how many ways can I pick 5 numbers if I have the numbers 1 to 30 on 1 lottery ticket? Again, this is going to be a combination because the order doesn't matter that we pick the numbers in. We have 30 to choose from. We're choosing 5. So when we find that combination, there's 142,506 ways to pick different lottery tickets, different numbers for it. Now, if you buy 1 ticket, what are your chances of winning? In that case, you have 1 ticket, so you have 1 chance of winning out of 142,506. Now, if you buy 100 different tickets, instead of having 1 chance of winning, you have 100 out of 142,506 different ways of winning. Okay, this is section 11.6, and we're going to look at events involving the word not and the word or, and we'll also look at odds of an event happening. So the probability that an event does not occur, or the complement of the event, is always going to be 1 minus the probability of the event happening. The probability that an event will occur will be 1 minus the complement of that event. So here we have, you're dealt 1 card from a deck of cards. Find the probability that you are not dealt an ace. Well, again, we'll start with our 1 because all probabilities are based out of 100%. And I know that in my deck of cards I have 4 aces. So I'm going to subtract the probability of drawing an ace. And to do this, I'll turn my 1 into a fraction. So I'll make it 52 over 52 minus my 4 over 52. And I end up with 48 over 52, or that simplifies to 12/13. So that would be my probability of not drawing an ace. Next, we have a heart. So we'll do 1, and remember your hearts are one whole suit, so it's 13 out of 52. So again, we'll do 52 over 52 minus 13 over 52, which will end up being, when I simplify it, I will end up with 3/4. And then probability of drawing a 3, again, there are 4 3s, so it will be that 1 minus 4 over 52, which would be similar to the problem up here. It's going to simplify to 12/13. So here we have a circle graph, and it shows the distribution by age group of 191 million car drivers in the United States. With all numbers rounded to the nearest million. If one driver is randomly selected from this population, find the probability that the person is not in the 50 to 59 age group. So let's find the 50 to 59 age group. Here's the 50 to 59 age group. Now I could add up all the other ones to find not in the 50 to 51 age group. Or I know that there's 191 million. So what I'm going to do is just do 1 minus 31 over 191, because it's 191 million. And then I will just convert that to 191 over 191 minus 31 over 191, and I end up with 160 over 191. So that's the probability that they are not in the 50 to 59 age group. And then next, they are at least 20 years old. So that means anything that is greater than 19 years. So if we look on here, they're at least 20 years old. The only group that is less than 20 is the less than or equal to 19, and that's 9 million people. So we're going to do 1 minus 9 over 191. And when we simplify that, or subtract, we get 182 out of 191. The rest of them are at least 20 years old. Okay, now here we're going to look at some events that are mutually exclusive, which means they don't have any overlap to them. These are events that cannot occur at the same time. So to find the probability that either A or, and keyword here is or, B occurs, you're going to add the two probabilities together. So if you randomly select one card from a 52 card deck, find the probability of selecting a 2 or a 3. Well, the probability of selecting a 2 we know is 4 out of 52, plus a probability of selecting a 3 would be 4 out of 52 as well. So the total probability when I add them together would be 8 out of 52, but that simplifies to 2/13. Next, we have a red 7 or a black 8. So we have 2 red 7s out of 52, plus, and then we have 2 black 8s out of 52. So when I add those together, I get 4 out of 52, or it simplifies to 1/13. Now here we have a mathematics faculty at a college that consists of 8 professors, 12 associate professors, 14 assistant professors, and 10 instructors. If one faculty member is randomly selected, find the probability of choosing a professor or an instructor. And when they say professor, they want straight professor, not associate or assistant, or an instructor. So first we have to figure out, well, how many faculty do they have at this college? So if I add 8, 12, 14, 10 together to get the total, I know I have a total of 44 faculty members. And we want a professor, so there are 8 out of the 44 that are professors, plus students, because we have the keyword or, and that means to add, an instructor, which there are 10 out of 44. So we end up with 18 out of 44. And then we can simplify it and make it 9 over 22. We're going to skip this next one because it has some overlap in it. We haven't talked about that. We'll do that on the next slide, actually. So we'll skip that one for now. So here we're talking about events that are not mutually exclusive, which means they have some overlap to them. So they can occur together. So the probability that A, and again, we have or B occurs. So we're going to add our probabilities together. We will do A plus B, but then we have to subtract the overlap or the intersection, what they have in common, because basically when we add these two probabilities together, we're adding in the common items twice, and we only want to add them in once. So here, we're going to start off with this one, and we'll go up here. The probability we are dealt a red card is going to be, so there are, out of the 52 deck of cards, there are 4 sevens, excuse me, so we have a 7 first, so there are 4 sevens. Now, red cards, there is half the deck is red cards because 2 of the suits, so it'll be 26 out of 52. But if we look, 2 of my 4 sevens are also red cards, so I counted them twice. My overlap then is going to be 2 out of 52 because 2 of my sevens are also red cards. So then when I do the math, I end up with 28 out of 52, which simplifies to 7/13. All right, next we have a heart or a picture card. There are 13 out of 52 hearts. Plus, and then picture cards, remember, are Jack, Queen, and King, and there are 12 out of 52. But when I look at those picture cards, the 12 that I included also include 3 of the hearts, the Jack of Hearts, the Queen of Hearts, and the King of Hearts. So I have to subtract 3 out of 52, my overlap. And when I do the math, that is going to give me 22 out of 52, which simplifies to 11 over 26. Now for our last one, we have a class of 50 students, 29 are Democrats, 11 are business majors, and 5 of the business majors are Democrats. So if one student is randomly selected from the class, find the probability of choosing a Democrat or a business major. All right, so we have 50 total students. And I know that 29 are Democrats. We have the or word there, so we're going to add. 11 are business majors. But 5 of the business majors are also Democrats, so we have to subtract our overlap of 5. And when we do the math, we end up with 35 over 50, which simplifies to 7/10. Okay, so here we're going to look at odds. And odds are the ratio of the probability that an event will occur to the probability that the event will not occur. So if you do odds in favor, you want to have the probability of the event occurring divided by the complement or it not occurring. If you do odds against, you want the probability of the event not occurring first over the event occurring. So we're going to start off, and a single roll or single die is rolled. Find the odds in favor of rolling a number greater than 2. So the probability of rolling a number greater than 2. Remember, your odds for a single die are 1, 2, 3, 4, 5, and 6. A number greater than 2 would be anything from 3 through 6. So that is 4 out of 6. And it's going to be divided by the complement to that. Well, the complement of that would be a number that's 2 or less, so it's going to be 2 out of 6. This is a compound fraction, so really this is what we have. We have 4 over 6 divided by 2 over 6. And then remember, we don't really divide fractions. We multiply by the reciprocal. So we'll do 4 over 6 times, and then we flip this second fraction, so we make it 6 over 2. And then, remember, you can cross simplify. So my 6's equal to 1. And if you want, you can just multiply straight across. We have 4 over 2. Or it simplifies to 2 over 1. So the ratio would be 2 to 1, or the odds. I have a 2 to 1 odds in favor of rolling a number greater than 2. Let's see here. If we look at, I'm going to skip this one because it's going to be the same as above. If we look at the odds against rolling a number greater than 2, here we had in favor of rolling a number greater than 2, and then you have against. To do the opposite of this one, all you do is take the reciprocal. So this is the odds in favor. The odds against would be 1 to 2. You really just take that reciprocal. Let's look here. We have one card is randomly selected from a deck of cards. Find the odds in favor of drawing a heart. All right, so find the odds in favor, and this should be of drawing a heart. So the probability of drawing a heart is, we have 13 out of 52. And then we're going to divide that by the odds against drawing a heart. So that's going to give us, if we have 13 out of 52, we have 39 out of 52. 39 cards are not hearts. So now we're going to do our division. We have 13 over 52 divided by 39 over 52. And we'll keep the first fraction as it is. Change my division to multiplication. Take the reciprocal of the second fraction. And you'll start to notice here, those denominators you can cross simplify those. We end up with 13 over 39, which gives me 1/3. So the probability, or not the probability, but the odds of drawing a heart out of a deck of cards would be 1 to 3. All right, then last one we're going to do is find the odds against drawing a 9. So if you think about our problem, we have 4 9s, but we want against drawing a 9. So if there are 4 9s out of 52, that means there are 48 cards that are not 9s. 48 out of 52 over 4 out of 52. So when we do the math here, we'll have 48 over 52 divided by 4 over 52. And then, so we're going to do 48 over 52 times 52 over 4. My 52s will cancel. We end up with 48 over 4, which simplifies to 12 over 1, or a 12 to 1 odds against drawing a 9. So now that we've learned about odds, what we're going to do is learn about how to take those odds, if you see them, and convert them into probability. So if you're looking for odds in favor of an event, you are going to take your odds. So if your odds are A to B, you are going to take them and you're always going to put the first number, A, on top, and your denominator is going to come from adding A and B together. So here we have the odds against a horse winning a race are 15 to 1. They want us to find the odds in favor of the horse winning the race, and then the probability of the horse winning the race. Well, the odds against are 15 to 1. So that means the odds in favor, remember, do your reciprocal, it would be 1 to 15. So then the odds in favor and the probability of the horse winning the race, this is going to be your A, this is your B. So the probability would be 1 over, and then add the two numbers together, so 1 over 16. Next, you are given the odds of 3 to 7 in favor of winning a bet, what is the probability of winning the bet? So again, 3 to 7, this is going to be A, this is going to be B. So it would be 3, and then you add the two numbers together, so 3/10. And then if you were given the odds of 3 to 4 in favor of winning a race, what's the probability of winning the race? So we have our A and our B, so it would be 3/7. All right, now we're on section 11.7. And here we're going to look at independent events, events involving the word and also conditional probability. So if events are independent and we're looking for the probability of A and B, that keyword and means to multiply the two events together. So here, a single die is rolled twice. So the first roll has no effect on the second roll at all. We want to find the probability of rolling a 2 the first time and a 3 the second time. So the probability of rolling a 2 the first time would be 1 out of 6. That and means to multiply. The second time it's a 3, so that's also 1 out of 6. And then when we multiply, remember you go straight across, so you end up with 1 over 36. Next, we have the probability that South Florida will be hit by a major hurricane in any single year is 1/16. What is the probability that South Florida will be hit by a major hurricane 2 years in a row? Okay, so any single year, the probability is 1/16. We want 2 years in a row. So the first year is 1/16. The second year is 1/16. The 2 years are independent. They don't have any, first year doesn't have any effect on the second year. So when I multiply it, I end up with 1 over 256. Okay, so here we're looking at the probability of an event happening at least once. So the probability that a region prone to flooding will flood in any single year is 1/10. So they want us to find what's the probability of a flood 2 years in a row. So again, we'll do what we did before. The 1 year doesn't have the outcome, like an effect on the next year. So it would be 1/10 times 1/10, which gives me 1/100. 3 consecutive years, we can take this as 2 years. So if I multiply it again by 1/10, we end up with 1/1000. Then they want the probability of no flooding for 10 consecutive years. Well, we know the probability that it will flood is 1/10. No flooding would be the complement to that event. So we would do 1 minus 1/10, which would give us 9/10. But we want that for 10 consecutive years. So really we need to do 9/10 times, or to the 10th power, because we want 10 years. And when we do that, we're going to get a decimal. And it's 0.348678. Now, then they want to know what is the probability of flooding at least once in the next 10 years. So if we know the probability that it doesn't happen, we can do the complement. So 1 minus that. So I'm going to take 1 and subtract the probability that it won't flood for the next 10 years. So minus my 0.348678. That's the probability that it will not flood the next 10 years. And the probability that it will flood in the next 10 years is 0.651322. Or if we looked at it as a percentage, we have about a 65% chance that it will flood once in the next 10 years. All right, so here we're looking for dependent events. And dependent events are dependent upon each other if the occurrence of one has an effect on the probability of the other. So here, dependent events, you're still going to multiply, but you're going to do the probability of A times the probability of B given that A has occurred. So we're always going to assume that A happens. And you can use this rule for 2 or more events. So for our first one, we're looking for the probability of getting 2 kings if you're dealt 2 cards from the deck. So you're going to get a card, they're not going to return it, and you're going to get another card. So the first time you draw a card, the probability of getting a king would be 4 out of 52. Then the next time, for the top number, we're always going to assume that we got our king. So it would be 3 because there's 3 left. And now there's not 52 cards, but there are 51 left. So when we multiply that, we get 12 over 2,652. Or if we turn it into a decimal, it's 0.00452. All right, next. There are 30 chocolates in a box, all identically shaped. 5 are filled with coconut, 10 with caramel, and 15 are solid chocolate. You randomly select one piece, eat it, then select a second piece. Find the probability of selecting a coconut chocolate followed by a caramel chocolate. All right, so we're going to start off with 30. And we want to select a coconut first. So there are 5 out of 30 that are coconut. We eat it. So that means now in the box there's only 29 left. And now we want a caramel chocolate. We're going to assume we got our coconut, but it doesn't really matter here. There are 10 that are caramel. So when we multiply this together, I'm going to simplify my 10 and my 30. I'm going to make that, divide them both by 10. So that becomes a 1. That becomes a 3. And when we multiply, then 5 times 1 will give me 5. And 3 times 29 gives me 87. So my probability is 5/87. All right, so here we have an ice chest that contains 6 cans of apple juice. Let's see here. 8 cans of grape juice, 4 cans of orange juice, and 2 cans of mango juice. So we're going to reach into the container and randomly select 3 cans in succession. So we're not going to replace them. We want to find the probability of selecting 3 cans of apple juice. So first we got to figure out, well, how many cans are in the container. But if we add 6 plus 8 plus 4 plus 2, we end up with 20 total. And 6 of them are apple juice. So the first time I reach in, I have a 6 out of 20 chance of getting an apple juice. Then we're going to assume we got an apple juice. I'm going to reach in again. Now there's not 20 left, there's 19. And there would be 5 cans of apple juice. And then I get another apple juice. So there would be 4 out of 18 left. And when we multiply these all together and simplify, like I can divide 5 into 20, and it goes once, that becomes a 4. And then we could do, like, make this 2/9. And we could divide this by 3, so it becomes 2/3. So when I do my multiplication, I end up with, oh, and I could do this, 2/4. So we can make that 1/2. And then 2/2 become a 1. So I have 1/57 when I get done. Now, if you're not sure about the simplifying part, just multiply straight across. Do 6 times 5 times 4, and then 20 times 19 times 18, and then simplify from there. All right, next we have a can of grape juice, and then a can of orange juice, and then a can of mango juice. So grape juice, there are 8 out of 20, and that's what I'm going to get first. Then I pull 1 out, so I only have 19 left. We want a can of orange juice. There's 4 orange juices. And then 2 out of 18 for the mango juice. And when we simplify this and multiply straight across, let's see here, we can divide 4 and 20 by 4. So that becomes a 1, that becomes a 5. And I can do 2/18, that can become, divide by 2, so that's 1/9. Then we multiply straight across. 8 times 1 times 1 is 8. And 5 times 19 times 9 will give us 855. So 8 out of 855. Okay, so here we're going to look at conditional probability. And conditional probability is the probability that event B happens given that A has already occurred. So your A here is always going to be your denominator. So when they do conditional probability, so we have these discs down here. We have red and yellow discs. So we want to find the probability of selecting a 3 given that a red disc is selected. And your keyword with conditional probability is given. So it says given a red disc is selected. That given is your A. That's your denominator. So we reached into the bag and we pulled out a red disc. So I have to count the number of red discs. There's 1, 2, 3, 4, 5. 5 red discs. So that's going to be my A. Now we want to find the probability of selecting a 3. So if I look at my red discs, they're numbered and only one of them has a 3 on it. So it would be 1/5. Now here, we want to find the probability of selecting an even number given that a yellow disc is selected. And for conditional probability, you want to look for that word given. So a yellow disc is selected. That's going to be my denominator. And I have 3 yellow discs. And then if I look at the yellow discs only, I want an even numbered one. So we have 2, 4, and 7. 2 and 4 are both even, so it would be 2/3 for my probability there. Again, the key word with conditional probability is given. Look for that word given, and then whatever's given is your denominator. It's what you're looking from to get the first part. All right, so we are on section 11.8 now, and that is going to be expected value. We're going to skip this first one because it doesn't really make a lot of sense with expected value. But what we're going to do for expected value, to find your expected value, you multiply each outcome. So we're going to look here at the number of girls for a family times the probability. And then you add all your products together. So we want to find the expected value for the number of girls for a family with 3 children. So the outcome of having 0 girls is a probability of 1/8. So we'll multiply that together and we get 0. Then 1 girl is 3/8. So when we multiply that together, we get 3/8. 2 girls is also 3/8. So when I do 2 times 3/8, we'll put that 1 underneath, it becomes 6/8. And then 3 times 1/8 becomes 3/8 again. So now we want to add them. And really what we're ending up adding, because the 0 doesn't matter, will be 3/8 plus 6/8 plus 3/8. So 3 plus 6 is 9. 9 plus 3 is 12. We have 12/8. Or if I simplify that, 12/8 is equal to about 1, or not about, but exactly 1.5. So here they're saying if you have a family with 3 children, you're expected to have 1.5 girls. Now, obviously, with this, just like when we have statistics that say every family has 2.1 kids, you don't have 0.1 of a child. You can't have half of a child. But that's what's expected to happen over time with families with 3 children. All right, so here we're going to calculate the expected value for an insurance company that shows like their premiums and how they calculate what you should pay for your insurance. So first thing we're going to do, again, you multiply to do the expected value, the amount of the claim times the probability. So we're going to multiply all these together and then we'll add them together. So this first one will be 0. Then if we do 20,000 times 2/10, it gives us 4,000. 40,000 times 600 will give us 2,400. 60,000 times 200 will give us 1,200. 80,000 times 100 will give us 800. And then 100,000 times 100 will give us 1,000. Then to find the expected value, or what we should pay for an insurance claim, or the average cost of an insurance claim, Add them all together, you end up with $9,400. So this is how much the company should charge everybody so that it breaks even on claim cost. Because even though most people they don't pay any money out to, we have other people that they do pay money out to. So when they average it out, this is what they're expected to pay to each person. Now, how much should the company charge to make a profit of $50 per policy? Well, if this is the amount they break even with, to make $50 per person, take your $9,400 and add your 50, so that would be $9,450. All right, and our last one here, we want to look at a game that's played using one die. We want to find the game's expected value if they charge $1.25 to play. And the game says, so our outcomes, here we're going to list outcomes, gain or loss, because we're really looking at, are we making any money or are we losing money over time? And then the probability. And because here we're talking about money, when we do the probability of the expected value, we're going to use our gain or loss times our probability here. So first, if I roll a 1, I win $1, and the probability of rolling a 1 would be 1/6. If I roll a 2, I get $2, and the probability of rolling a 2 would be 1/6. If I roll a 3, I end up with $3, and that's 1/6. But then if I roll a 4, a 5, or a 6, the probability, or the gain or loss, I get $0. And that probability is going to be 3/6. So when I multiply those together, 0 times 3/6 is 0. 3 times 3/6 will give me 3/6. 2 times 1/6 will give me 2/6. And 1 times 1/6 will give me 1/6. So when I add those together, I'm going to end up with 1 plus 2 plus 3 will give me, so I'm going to add all these together. I get 6/6 or 1. So that means over time, I'm expected to gain or get $1. But what we also have to look at is we have to pay to play. We have to pay $1.25 per game. So per game, overall, expected value, I'm expected to win $1. But if I have to pay $1.25, and I calculate that in, then really my expected value is going to be negative 25 cents. Which means, really, over time as I play the game, I'm not expected to win any money. I'm expected to lose 25 cents per game.